Imagine a world without electric lights or refrigerators.
Without computers.
Or even your smartphone.
That wasn't that long ago.
Welcome to Xul Podcast, Shooting the Reality, where we take all those articles and research and notes you've got stacked up.
And we distill it down to the essence of what you need to know.
I'm James Caro.
And I'm Emily Lora.
Today we're diving into electricity.
The force that shaped our world.
We're going to explore how we went from, just noticing static to harnessing this force that powers everything.
Yeah, all the tech that's revolutionized how we live.
I'm looking at all this research we've got here. It goes all the way back to ancient Greece.
I know. It's amazing to think that it all started with simple observations, not even in a lab.
Yeah, like 600 BC.
Thales of Miletus.
The so-called first scientist.
Right, rubbed amber with fur and it attracted feathers.
Static electricity.
Exactly, our first documentation of it.
I mean, that stuff is just annoying today.
Right.
Static cling.
But back then it was a total mystery.
What do you think Thales would say if he saw what we do with electricity today?
I can't even imagine, but his experiment sparked this journey of discovery that's lasted for millennia.
The ancient Greeks were really into it.
Oh yeah, they even got the word electron.
From their word for amber.
Electron.
And that turned out to be the name of the particle responsible for electricity.
It's incredible.
And at the same time, you've got the ancient Egyptians.
Right, using lodestones for navigation.
Those naturally magnetic minerals.
Exactly. And even though they didn't know how magnetism and electricity were connected, they were already using this relationship.
So every civilization had its own electricity encounter.
It seems like it.
And it's fascinating how, for centuries, it was just this mystery force. When did we start to actually get it, scientifically?
That shift starts in the 17th century with William Gilbert.
Oh, right.
Physician to Queen Elizabeth I. He actually coined the term electricity.
From the Greek word for amber.
Exactly, and he was one of the first to say that it could flow like a current.
So he set the stage for all this scientific exploration to come.
He really did. And then in the early 18th century, Charles Dufay made a huge discovery. There are two types of electricity. Vitreous and resinous, based on what he was using to make them.
And we now know those as positive and negative charges.
That's right. And he saw that, charges repel and opposites attract.
Electrostatics.
One of the fundamentals.
Dufay really shifted things from just observing to, really trying to understand it.
Absolutely. And around the same time, you have Benjamin Franklin.
Oh, yeah.
A true Renaissance man.
The famous kite experiment.
I know, super dangerous.
Flying a kite in a thunderstorm to prove that lightning is electricity.
I wonder what his insurance premiums were.
They must have been through the roof.
But all kidding aside, that experiment showed there's one electric fluid with positive and negative charges.
Didn't some people think there were two fluids?
Yeah, there were definitely some disagreements back then.
Like William Watson, he was all about the single fluid idea.
Right. And Robert Simmer was in the two fluid camp.
Those debates were so important for figuring things out.
I agree.
So we've got charges and current.
Right.
But how did scientists actually study electricity back then?
Well, that's where the Leyden jar comes in.
Okay.
Invented around 1745 by Peter van Musschenbroek.
Yeah.
It was the very first electrical capacitor.
A way to store charge.
Right. So scientists finally had a reliable way to experiment.
It's like a mini power source just for experiments.
It really opened up the field.
And then scientists started looking at the connection between electricity and living things.
Right. The frog leg experiments.
This is like Frankenstein stuff.
I know, right?
Late 18th century, Luigi Galvani,
Italian physician,
saw that frog legs twitched when they were near static electricity or even just different metals.
And that gave him the idea of animal electricity.
Like electricity is part of living things.
That was his theory, but Alessandro Volta, another Italian scientist, challenged that.
Oh, so he didn't think animal electricity was real?
Nope. He said the frog legs were just reacting to the electricity from the metals touching.
So he debunked that whole thing, but what did he do?
Well, he used that to create something groundbreaking, the battery.
No way.
The voltaic pile, a stack of zinc and silver discs separated by cloth soaked in brine.
The first reliable source of continuous current?
Exactly.
That must have been a game changer for scientists.
It absolutely was. It really kicked off a ton of new research.
And that takes us to Hans Christian Ørsted, a Danish physicist who in 1820 made a discovery that changed everything.
It was a huge turning point.
Like another one of those accidental discoveries.
Kind of. He was giving a lecture and had a compass near an electric wire.
Okay.
And when he switched on the current, the needle moved.
So he was able to affect a compass just with electricity in a wire?
That's right. It was the first clear link between electricity and magnetism.
Wow.
What we now call electromagnetism.
Okay.
He realized that the current created a magnetic field, and that's what affected the compass.
That's huge.
It really was like these two separate forces were suddenly connected.
And that discovery must have been huge for the scientific community.
It caused an explosion of research scientists everywhere were trying to figure out this connection.
I can imagine the debates and the competition.
Oh, absolutely. And André-Marie Ampère, a French physicist, was one of the scientists who jumped right in.
Okay.
He really took Ørsted's observations and ran with them. He wanted to really understand how they were related.
So what did he do?
He set up all these experiments with wires and compasses to look at the forces between currents and magnetic fields.
Okay.
And he showed that parallel currents attract each other, and currents flowing in opposite directions repel each other.
So it matters which way the current's going.
Exactly. And he even came up with a mathematical law.
Okay.
Ampere's law. It describes how strong the magnetic force is between two wires with current in them.
So that explains how electricity makes magnetic fields and how those fields can affect each other.
Exactly.
This is bringing back memories of high school physics.
Right.
We've gone from static and frog legs to like a fundamental law of physics.
It's pretty remarkable how fast things were moving.
And it wasn't just theory. It had the potential for real-world applications.
Absolutely.
So if electricity can create magnetism, can it create motion?
And that's where Michael Faraday comes in.
I've heard of him.
This brilliant English scientist, completely fascinated by Ørsted and Ampere's work. He had this vision of electricity powering machines doing real work.
Did he invent the electric motor?
He did. In 1821, he built this device that showed how electrical energy could be turned into motion.
So from a twitching compass needle to a spinning motor.
That's progress.
But I bet Faraday didn't stop there.
You're right. About a decade later, he made an even bigger discovery, electromagnetic induction.
Okay, what is that?
Imagine you have a coil of wire and a magnet.
Okay.
When you move the magnet through the coil, you make a current in the wire.
So you can make electricity just by moving the magnet.
Exactly. No battery needed.
Incredible.
And that discovery led to the electric generator.
Amazing to think we could make electricity without relying on batteries.
Right. We could generate it on a larger scale enough to power homes and cities.
So that's where the idea for power plants comes from.
Exactly.
But batteries, motors, generators, they all need energy to work.
Right. Where does that energy come from?
That's a good question.
And that brings us to James Prescott Joule.
Another important name.
An English physicist totally devoted to understanding energy.
Oh.
And through his experiments, he came up with the law of conservation of energy.
Remind me what that is.
It says that energy can't be created or destroyed, just changed from one form to another.
Got it.
So like when a battery powers a light bulb, chemical energy becomes light and heat.
So there's no free lunch with electricity. You have to put energy in to get it out.
Exactly. And Joule showed us that we need to find good ways to turn other energy sources into electricity.
And that's where power plants come in. They use coal, oil, natural gas, nuclear, and renewables to make electricity.
Right.
So now the story of electricity starts connecting to our modern world.
Yes, we understand it, we can generate it, and we know we have to find efficient ways to make a lot of it.
But the story doesn't end there.
It doesn't.
We've got electricity and magnetism connected. But what's the thing that connects them? How does it actually work?
That's where we need to talk about James Clerk Maxwell,
Oh.
a Scottish physicist, a real mathematical genius. And he changed everything we thought we knew. A brilliant mind who brought together centuries of research on electricity and magnetism
Into one elegant theory.
Exactly.
Laying the foundation for a tech revolution that is still shaping our world.
Absolutely. In the 1860s and 70s, Maxwell took everything scientists knew
About electricity and magnetism.
and he wove it into this set of equations that completely changed how we understand these forces.
Okay, so equations, mathematical wizardry.
I know it sounds a bit intimidating.
But what did he actually figure out?
Essentially, his equations describe how electric and magnetic fields are intertwined.
Okay.
They show that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field.
So they're constantly influencing each other.
Yeah, like a feedback loop of energy.
That's pretty profound.
It is, and here's where it gets even crazier. Maxwell's equations didn't just describe these interactions,
Right.
they actually predicted something totally unexpected: electromagnetic waves.
Electromagnetic waves?
Yeah.
What are those?
Okay, imagine those ripples that spread out when you throw a stone into a pond.
Okay, I can picture that.
Maxwell's equations predicted that changing electric and magnetic fields could create those same kinds of ripples,
Okay.
but as waves of energy radiating outward.
So these invisible waves of energy are just shooting out.
Right.
But how does that affect us?
Well, Maxwell calculated how fast these waves would travel.
Yeah.
It turned out to be the speed of light.
Wait, are you saying that light is an electromagnetic wave?
That's exactly what he proposed. His theory brought together electricity, magnetism, and optics,
All into one.
showing that light is just a self-propagating wave of electric and magnetic energy.
So everything we see, all the colors and light around us, are just different frequencies of these electromagnetic waves.
Exactly, and that realization changed everything, because if light is an electromagnetic wave, then there have to be other types of electromagnetic radiation out there at different frequencies.
Like radio waves and microwaves.
Yes, and X-rays and gamma rays, the whole electromagnetic spectrum.
Wow.
Maxwell's theory gave us the framework for understanding and using all these different kinds of radiation.
That's a huge deal.
It was a revolution, but it took a while for everyone to accept it.
I bet it was a pretty radical idea back then.
It needed some experimental proof.
So who proved it?
About a decade after Maxwell died, a German physicist named Heinrich Hertz built a device that could create and detect electromagnetic waves.
That's amazing.
It was confirmation of Maxwell's predictions, and it ushered in the age of wireless communication.
So that's where radio comes from.
Exactly, inspired by Maxwell's theories.
It's incredible to think about how one person's ideas could have such a huge impact.
Maxwell's theory was a testament to human ingenuity and our drive to understand the universe.
And it led to technologies we use every day.
Absolutely.
From Thales rubbing amber to Maxwell's equations to Hertz's radio waves, we've come a long way.
We have, but the story isn't over.
It isn't.
As scientists dug deeper into electricity, they started exploring the atom itself. They're trying to figure out what those particles are that actually carry electric charge.
Okay.
And that led to the discovery of the electron by J.J. Thomson in 1897.
So electrons, those tiny particles, are the key to electricity.
Exactly. They're what flows through wires, creating the currents that power all our devices.
And then our understanding of electrons led to transistors, integrated circuits, and basically all the electronics we have today.
Exactly. Solid-state physics is what we call it.
It's incredible to think that our smartphones, the internet, all of it came from rubbing amber with fur thousands of years ago.
It really shows the power of human curiosity and our drive to understand the world around us.
So what does it all mean?
From those ancient sparks of curiosity to the intricate dance of electrons, our understanding of electricity has come a long way, and it's a story that's still being written.
I wonder what the next big breakthrough will be.
It's an electrifying thought.
It's been an incredible journey.
It really has, from static electricity and frog legs
to this grand unified theory of electromagnetism.
It's a testament to human curiosity and our constant search for knowledge.
What an amazing deep dive.
It makes you wonder what the next big discovery will be.
What other mysteries are out there waiting to be unlocked?
It's exciting to think about.
It really is. We'd love to hear your thoughts on this incredible story of electricity.
Subscribe to Xul Podcast, Shooting the Reality, and leave us a comment.
Tell us what sparked your curiosity.
Until next time.
Keep those brain circuits firing.
Ah!